Okay, so first of all, I would like to thank the organizers for organizing this workshop and for this opportunity to present my results here. And I would like also to join to congratulations to Valentin Ivanovich. And I would like to say a couple of words. I was working in the same laboratory in Moscow ITEP with Valentin Ivanovich. And actually, when I was a student, I was at the course of Valentin Ivanovich. This was about some non-productive aspects of QCD. Actually, it was the first time when I met with this chiral effects, anomalous transport, and this. I remember this lecture pretty well. I don't remember a lot of from this time from a lot of lecture, but this particular lecture I remember pretty well. This was a very nice and clean introduction to this magnetic effect. So let me congratulate and wish all the best, good health, new scientific achievements, and good students. Now let me turn to my presentation, and I would like to discuss chiral magnetic effect and our work, which was aimed at the study of the chiral magnetic effect, and in particular of one of the of its manifestations, as which can be seen from conductivity of quark-Gluon plasma in magnetic fields, not only of quark-Gluon plasma. Let me probably start with some very general introduction, which might be known to the major part of the audience, but still, let me just probably remind you. So what is non-zero chirality, and why is it interesting to discuss this thing? So if we take quarks or some particles near the massless, then they have spin, and in the massless or chiral limit, we can call some of them right-handed, some of them left-handed, depending on the projector of spin on their momentum. And if there is a difference between this between the number of left-handed and right-handed quarks, then we call this difference of densities the chiral density, and we would like to discuss this non-zero chiral density into details. It turns out that this non-zero chiral density can be created in some systems of interest, in particular in heavy ion collisions. There are several mechanisms, including parallel electric and magnetic fields, or ferroelectric and ferromagnetic fields, and including some fluctuations, gluonic and fermionic. We might have some talks about it later during this session, or probably during discussion. The point is that this non-zero chiral density can be created, and this is the famous suggestion, the famous idea that if we have non-zero chiral density and the system is in external magnetic field, then it's just very natural to expect an electric current along the direction of the field, according to very simple formula. This very simple formula. So the current status, as far as I know, of this effect is much more debatable and much more subtle. The point is that from experimental side of view, when one takes into account all background effects, noise, and so on, then the results become compatible with zero. On theoretical side, there are also some issues which are related to the fact how one defines non-zero chiral density or non-zero chiral chemical potential. One can do this in a static or dynamical way, and depending on the subtleties, one can get different different answer. So what I would like to discuss further in my talk is that the so-called dynamical chiral magnetic effect, which is manifested through electromagnetic conductivity of medium. Electromagnetic conductivity of quark-gluon plasma is a very interesting thing on its own. So we have a very simple formula from the school that this is just the coefficient between current and electric field. And it turns out that first of all, there can be large electric fields created in heavy ion collisions. In particular, when there are some asymmetric collisions of two various nuclei that carry various electric charges, then there can be non-zero electric fields, and this can lead to some asymmetric flow. The value of the conductivity can be used in the simulations of on how electromagnetic field evolves with time. Like, for example, large values of this conductivity can lead to large relaxation time of magnetic fields creating heavy ion collisions, and also it is related to some observables like photon rates or dilepton rate, etc., etc. So this quantity is also interesting to study on its own and in the context of heavy ion collisions. Now, let me try to unite all these things that I discussed and to say why it is interesting to discuss this conductivity from the point of view of chiral magnetic effect. Let us look at the external, at our system, and suppose that we put it into external magnetic field. And let me discuss how this external magnetic field changes the properties of this medium. So in order to discuss conductivity, one has to turn on external electric field so that we have our medium, which is put under the influence of external electric and magnetic fields. Now let's look what happens. So due to the chiral anomaly, the derivative of the chiral density with time is proportional to this term, this scalar product of electric field and magnetic fields, just anomaly. And of course, we know that chirality is decaying with time. So in the first approximation, we can add this term proportional to rho phi, which is just relaxation towards zero value of rho phi due to chirality change in process. The tau, this coefficient tau, we call chirality change in scattering time. So then, if we have external electric and magnetic field, then the system would naturally stabilize at the zero value of d rho 5 over dt, which is given by zero value of this quantity here, so that we have rho 5 proportional to scalar product of E and B times this chirality change in time times this non-important coefficients at the moment. And now, since we have non-zero chiral density and we have magnetic field, one can naturally expect that there is this chiral magnetic effect. And we can use this formula, which I showed a couple of slides before, that electric current is just mu5 times magnetic field. In order to use this, the only thing that we should do is just to plug the dependence of rho 5 on mu5. It turns out that there are different regimes. If we have small magnetic fields, then rho 5 is naturally proportional to mu5 temperature squared. At large magnetic fields, the behavior changes to mu5 times b. So that in these two different regimes, we have different expressions for mu5, which differ just by this prefactor here. Nonetheless, we can plug any of these two expressions in the expression for the CME current, and then what we get is this additional term to the electric current proportional to mu5 and magnetic field. Plus, we have ordinary ohmic conductivity given here by this term. So now what we see from here, we see that there is an anisotropic phenomena. If E and B are perpendicular, then this scalar product is zero and this term is zero. If E and B are parallel, then mu5 is proportional to electric field, and we have additional term here proportional to electric field, so that there is an additional contribution to chiral magnetic to conductivity, which we call CME conductivity, given by this simple expression. And this is the manifestation of one of the possible manifestation, rise of the conductivity with magnetic field. Here, I would like to stress one important thing, that if we take a classical system, so we just take a classical gas of charged particles and put it in external magnetic field, then classically magnetic field shouldn't change their conductivity along its direction, because if particles go along magnetic field, there is no Lorentz force, so they just simply don't feel this magnetic field. That's why this is this effect is purely quantum effect. So classically, it is zero, and this simple this effect can be observed in condensed matter. In Dirac-Weyl semimetals, it was observed experimentally. So this is the inverse of the conductivity as a function of magnetic field, and it indeed decreases, so that conductivity increases with magnetic fields. And also it was observed in quantum Monte Carlo simulations of these condensed matter materials. Even of those, both these regimes were observed. So the question is, what happens in QCD? Can we say something about QCD, whether this happens there or not? Here we would like to study this by means of lattice simulations. The parameters of our simulations, some technical details for those of you who are interested. So we have 2+1 quarks at physical masses of UD and S. We are working in the deconfinement phase at two temperatures, 200 and 250 MeV. And we also made some check of the lattice artifact by performing simulations at two values of lattice step at temperature 200 MeV. I'll discuss a bit later why we are doing this only in the deconfinement phase. Now let me say a couple of words about the conductivity and how this is measured in lattice simulations. This is this is something from some point of view very simple, from another point of view very complicated thing. The basis of the method is the Kuber formula or Kuber relation, which relates transport coefficients like conductivity to some correlators. In particular, in terms of electromagnetic conductivity, one should look at the correlator of electromagnetic current, like given by this expression here. But it turns out that this nice formulation is valid only in Minkowski space, so one has to take zero spatial momentum and take this limit at zero frequency momentum. But it is very nicely performed in Minkowski space. So one can introduce the so-called spectral function, which is just the imaginary part of the retarded Green function, and its zero frequency behavior gives just our conductivity. In order to extract this somehow from the lattice simulations, one has to make analytical continuation. And after analytical continuation, the relation becomes a little bit more complicated. if one measures on the lattice the correlator of electromagnetic current, then it is related to the spectral density via this famous relation, integral relation, with this kernel here, and this gives us the Euclidean correlator. After inversion of this relation, one can extract the spectral function, and one can extract the conductivity by its zero frequency behavior. So now let me discuss the properties of this spectral function and say a couple of words on how it can be extracted from lattice simulations. It turns out that the properties of this spectral function, there are a lot of properties of the spectral function which one should take into account. I think the most important ones are the following. First of all, one knows the behavior of the spectral function at small frequencies. This is just conductivity times omega, and at large frequencies, since QCD is an substantially free theory, at large frequencies we expect that one can apply perturbation theory, and the simplest expression perturbative is just omega squared times the spectrum. And there are intermediate, probably some intermediate peculiarities, like some Rho-meson peaks, which should be present in confinement and might be dissociated in the deconfinement phase. Probably some other details as well. In order to invert this relation, we use the Backus Gilbert method to do this. I won't go deeply into details of this method. The most important thing is that it gives not the true spectral function, but instead of this, this method gives a convolution of true spectral function with some kernel, some function which is called a resolution function delta omega omega hat. This method tries to make this function as close to the delta function as possible, so that these two functions are very close to each other. But of course, it is not possible. So the characteristical widths of the spectrum function can be reached from this plot here, from these blue lines here. It is of order of several temperatures, like four temperatures. So one important thing which I would like to say is that in this method, before applying this method, it is very important to estimate the ultraviolet part of the spectral function and to subtract it. Of course, one can just simply write this very simple expression, perturbative, that this is an omega squared, simple omega squared. But it would be nice to somehow confirm and to see when this behavior starts. It turns out that it is very difficult to estimate it model independent. In previous works, the authors where people try to study the conductivity without magnetic field, they try to fit it by some ansatz, and it turns out that indeed this can be this simple form works starting from like 7 temperatures. We also made an additional reconstruction at 0 temperature and checked that indeed at large frequencies or at small distances this approximation works. And we made a subtraction starting from 1.5 GeV up to from omega naught 1.5 up to 3 GeV, so that this contribution of this ultraviolet part isn't present in the final estimation. But here I would like to stress that it is an additional source of uncertainty, an additional subtlety in our calculations. So now let me turn on to results. So if you're not interested in the technical details, so this is the point where I go to the results and I discuss what we obtained. On this plot, we presented the conductivity of zero magnetic fields as a function of temperatures compared to results of other groups. I would like to stress that we were the first ones who performed simulations at physical iron mass. It turns out that properly normalized our results are in agreement with previous groups. So it means that the non-zero iron mass or larger iron mass might not affect the quantity, uh, the uh, the conductivity and its value. Uh, and also, I would like to say that these 2 points are our results at 2 lattice spacings, and they agree with each other within error bar. So we expect that finite the lattice artifacts are small. Now let me discuss what happens at non-zero magnetic field. In order to avoid all these subtleties with ultraviolet tail, uh, we looked at not at the conductivity, but at the difference of the conductivities at zero magnetic field and non-zero magnetic field, or the difference in the spectral function, or in the difference at the correlator. Since we are working with this Backus Gilbert method, which is a linear one, um, it is it is um, it is um, uh, one can apply this method for the difference, and since it is linear, we can get some results about it. So what we have here is on this plot is the change of the spectral function in parallel to the magnetic field direction as a function of frequency for several values of magnetic field starting from small 0.28 GeV squared up to very large. And what we see is that the low frequency part is significantly enhanced when one increases magnetic field. Uh, so at large values of magnetic fields, this uh, this low frequency part, which corresponds to conductivity, is large. We can convert it into the conductivity itself, and this is the final result of the conductivity as a function of magnetic fields of both parallel and perpendicular directions. So these points that are going down correspond to perpendicular directions. These points that go up correspond to parallel direction. These points correspond to 200 MeV, temperature 200 MeV, and 2 lattice spacings. And these points correspond to slightly higher temperature, 250 MeV. So we see that for both temperatures, there's a nice clean growth of the conductivity with magnetic field. So we observed this chiral magnetic effect. This decrease of the conductivity in perpendicular direction is a phenomenon of magnetic resistance. It can be also easily understood from some classical arguments of particles going in perpendicular magnetic and electric fields. Based on the slopes of these dependencies, we can extract uh, the chirality relaxation time. It turns out that it is of approximately 0.25 Fermi divided by the speed of light at both temperatures. And it is a nice agreement with the results obtained by means of effective models of QCD. So finally, it is also interesting to discuss the contribution of various quarks to conductivity. It turns through this chiral magnetic effect. Naively, the contribution of various quarks should scale as q to the cube, because there are factors from magnetic fields, interaction from magnetic fields, and there are factors from the correlator of electric currents. That's why if we take this CME conductivity divided by q to the cube and look at this, and it turns out that all 3 quarks, U, D, and S quark, they are more or less in agreement with each other. There is some deviation between U and D and S quarks, which might be somehow attributed to more complicated effects of various quark charges. But the masses and the large mass of the quark doesn't influence this conductivity. And finally, I would like to discuss. Another work where there was previous work where this effect was also studied, the conductivity of Quark-Gluon plasma in external magnetic field. And it turns out that in this paper, the authors obtained different results, that there is no chiral magnetic effect in Quark-Gluon phase, and there is chiral magnetic effect in the confinement phase. It might be that the difference between their results and ours can be attributed to the following facts. First of all, the magnetic fields which they studied are much lower than ours, so it might be that they in the deconfined phase they simply didn't go very far from this zero magnetic field limit. And in the deconfinement phase, the effect is much more complicated. It turns out that in the confinement phase, the spectral function contains a lot of peculiarities. There are some peaks related to raw mass, and there can be some mixing between various masses. And most likely it is very difficult to disentangle the contribution of all these effects from the effect on the conductivity. So that's why confinement phase. Now let me come to my conclusion. Maybe from the first formulations, the first calculation of the conductivity in quark in QCD at physical biomass, we observe large magnetic conductivity in parallel direction to magnetic field and magnetic resistance in perpendicular direction, and the results are consistent with chiral magnetic effect in this dynamical formulation. Thank you for your attention.
Okay, thank you, Andrey, for the interesting talk, which is now open for discussion. Please use the option to raise the hand or just to unmute your micro and ask. We still have time. Just thank you also for being quite in time. Maybe in the meanwhile, just I can make just a comment that you mentioned the relation to the emission of soft photon, but also just it can be related to emission of dileptons. Generally soft, of course, but well, if being a bit optimistic. And just it's the existence of just conductivity component of conductivity parallel to the magnetic field corresponds to longitudinal polarization of lepton pair, corresponding to that on the same direction. And this is exactly what is currently observed by Alice collaboration. So it's not excluded that polarization of, it is studied for vector mesons for just higher masses of dileptons. But what happens that some lattice calculations for vector mesons, they produce more or less similar situation. That also polarization is longitudinal. So maybe it's manifestation of the dynamic chiral magnetic effect in the tensor polarization of vector mesons and lepton pairs. So this is just my comment.
Yeah, thank you. It would be probably very interesting to somehow compare their predictions.
Maybe in fact, well, actually, of course, this should be if associate just the lepton pair with your correlator completely. Just this difference between longitudinal and the transverse conductivity is straight related to the angular coefficient in a straightforward way. But maybe, just maybe, just it's the question is whether it's a complete expression or. Maxime, please.
Yeah, hi. I would like to ask a question. Maybe I mean, just a comment. Maybe the difference is related to the fact that we, in that paper, we considered actually the quenched SU2 theory, quenched. And you consider now the real QCD with the 3 quarks and the dynamical ones, and the effects can be, the difference can be due to that.
Yeah. Thank you for this comment. It could be so. Still, I think that at least in the deconfinement phase, it is. In the confinement phase, this is very difficult to disentangle all these effects. So that there is this Rho-meson peak, and it can be shifted by magnetic field, or it can become wider, narrower, and it. So we tried it, and it is. I would say that it is very difficult to say whether so one should use probably some additional information or perform some simulations at very large lattices in order to disentangle whether the change in the correlator comes from this Rho-meson or from.
Okay.
But in principle, yeah, this can be also somehow related to this the fact that this wasn't quenched.
First paper, simplest one in this direction as far as I understand. That's why it can be. It may have some errors. I mean, our papers, not errors, but kind of simplifications. It has some simplifications which were not available at that time. So we did not have dynamical QCD at that time. It was more complicated.
It would be quite interesting if really the difference is because of that. So it's entirely some effect of unquenched, right? So
yeah,
just
it's but it's interesting. Of course, one should think about that. It's a very interesting question.
Yeah.
Okay.
So more questions, comments. Well, we just may continue just in the discussion session. So let us thank the speaker again.